Thank you, Ms. Srinivasan. Okay, moving right along to the next presentation, which is about quantum computing. As we all know, it's a rapidly increasing technology that harnesses the laws of quantum mechanics to solve problems too complex for a classical computer. We are delighted to invite Dr. Rohini Srivathsa, National Technology Officer, Microsoft India, to deliver a session on software stack designs for quantum computing. May I please request everyone to give Dr. Srivathsa a very warm welcome.
Hello, can you all hear me? Great. First of all, I'm a big fan of Dr. Pramod, so I am just so honored to be following him. And all the work that is happening on digital public goods in India Stack is just absolutely inspiring, absolutely inspiring. But I will shift gears a little bit to talk about quantum computing. How many of you have heard about quantum computing? Just a show of hands. How many of you know what it is? Okay, and how many of you have, I guess, how many of you have used quantum computing or worked on quantum computing? All right, so that's useful because then I will kind of, keep it at a way that you can get something out of this session and not just hear a lot of buzzwords, okay? All right, so I am trying to use the, okay, great. All right, so it went back. Okay, great. Okay, so I'm sure there's a lot of hype that you must have heard about, this quantum computing is coming, and are you a part of it, and are you part of that race? Maybe it's already there, et cetera, et cetera. I think it's very important for us to realize, first of all, what quantum computing is, and what is the current state of it, practically speaking, and therefore, what should be the call to action? What should we do about it? Because while it is a very, very transformative and completely disruptive way of computing, it has a lot of technological challenges that are yet to be overcome. And yet, because it is such a fundamental paradigm shift, those of us who are in the world of computing and software need to get ready for it early on. So my intent for today's conversation would be to get really, really practical, to help you understand where we are today and how to think of an overall stack approach to quantum computing and what should you do today. Now, it's a bit esoteric, but let's go on this journey a little bit, okay? There are words out there in terms of saying what all quantum computing can solve. Because quantum is actually the real nature of the universe. Reality is quantum. In fact, I would go as forward to say that our standard computing, classical computing that we have on our phones, on our computers, everything else, is really a special case of quantum computing. So quantum computing is actually how nature behaves. That's what Richard Feynman said, that nature is quantum. Can I somehow harness how nature behaves at the subatomic level to do computing? Now, I began my career almost 30 years back in the world of semiconductor design, working at very, very small devices levels, thinking of electromagnetic effects at sub-micron, deep sub-micron technologies. And I'm telling you, even at that time, we were starting to wonder what will happen when these electrons and these sizes become of the size of an atom. Okay, and today it's much, much, much more smaller. So the point is that it's, from a physics perspective, it is where we will have to go. But what does that mean? And if you go there, then you will be able to solve a certain kind of problems which require you to understand the physics of how nature behaves. For example, when you think about fertilizers, the problem that a fertilizer is trying to fix is carbon fixation. It is trying to take carbon and create nutrition out of it. carbon fixation is a chemical process. To understand how to create fertilizers that are more effective, less expensive in terms of water resources, etc., scientists need to understand the molecular behavior of carbon fixation at the molecular level. Similar problems are there in many other areas, such as energy efficiency, superconducting, pharmaceutical drug discovery, and many such problems are there. These problems today's computers cannot solve because they grow exponentially. So what happens is that if you take a molecule, even a molecule as much as a coffee, a caffeine molecule, and try to simulate a caffeine molecule today in all its quantum behavior, you actually cannot. Because the exponential nature of it is not possible. So what I'm showing here is, as the problem size of some of the examples I gave you increase, your normal computing exponentially grows so fast that, the words I will use are somewhat little bit, the age of the universe is not enough to solve some of these problems. Okay, you can compute for as long as the universe has existed. You're not going to be around for that long. So I think what quantum is a completely different paradigm shift. It changes some of these exponential problems to linear. But that's not a magic wand, okay? There's a lot of issues to be solved there. The reality is that to get something to really be useful, even to have some level of scientific understanding of molecules, of carbon fixation, of drug discovery, etc., you need qubits, at least 100,000 qubits. You look at any press, we are talking of the order of few hundred qubits, couple of thousand qubits, right? So even for good scientific understanding, you need 100,000 qubits. Now, to actually have anything practical that is getting solved using quantum computing, you will need at least 1 million qubits. Now, qubit is the equivalent of a bit. So I hope you realize that the computers you're using, underneath there are bytes, and each byte is made of 8 bits. Equivalent of the bit in the quantum world is something called a qubit. And the interesting thing about a qubit, which is why the whole quantum computing world works, is that a bit is typically a bit is either in a 0 state or a 1 state. A qubit, interestingly, is both 0 and 1 at the same time. That sink in. It is both 0 and 1 at the same time. That's called superposition. There are other behaviors in quantum physics, like interference, like entanglement, which is the fundamental way in which nature behaves. That is the nature of reality. But the point is that to get these qubits to be stable to do any real computation is non-trivial, because they dissipate and take a what they call they take a standard bit state. They don't remain in the superposition state. Anyway, the point being that right now we are quite far away from having a computer that is actually useful from a standard number of bits perspective. I hope I'm not losing everybody. Okay, so the number of qubits you need, so the takeaway is very simple. The number of qubits you need, which is equivalent to a bit, to solve any real problem is more than 1 million. We are very far from that. From a pure R&D perspective, hardware perspective. Where we are today is something called a NISC world. It's called noisy intermediate scale computation. What it means is there are certain number of bits, qubits, which are noisy, and there is a way of doing some kind of an error correction on them and do some quantum computing. But there's a lot of research happening around the world, in academia, in industry, in government labs, all around the world, right? So while all that is happening, and we know why we need it, we will need something like quantum computing to solve, or we will need quantum computing, at least of that order of complexity capability to solve some of the real problems we are seeing around the world: hunger, climate change, water, right? Some of these big problems. But we are not there yet. So what does that mean? That means that in the interim, there has to be a better way to, one, harness what we have, and two, prepare for a world where quantum computing will be available at scale. So how does one do that? I'll give you a Microsoft point of view, but take that as a view of the industry, at least in some respects. The way we are thinking about it has to be a horizon approach, meaning that at the end of the day, you're not going to give a full problem to a quantum computer, meaning you won't have a quantum computer that does addition, subtraction, and basic things that your current computers do. It's going to be a very special purpose computer, which is why the title of this talk is about quantum computing from a software stack perspective. Because when you think of a software stack, you are able to think about the fact that this is a part of that stack. How do you prepare the rest of the stack in a way that you can prepare for large-scale quantum when it happens, and yet along the way get some benefits? So I'll just talk about the fact that there are sort of three horizons. The first one is about saying that there are certain hardware capabilities that are available today, and that you can improve classical computing in some ways. There's a portfolio of ecosystem that we are putting together, and while we are working on simulations and quantum computing using simulations. As we go further, there are certain kinds of quantum approaches that are coming up, like topological computing, etc., and we go further. But let me not belabor on this too much. Let's move forward. So if I said today, if you were to, those of you who are into computation, architects, and thinking about, where does this play for me at all, there are two directions we are taking. One is quantum computing, and the other is optimization. Let me talk a little bit about both of them, and I'll sort of give you a sense for how best you should start. So when we say quantum computing, what we are talking about is, while there is a hardware, there are languages and there are software development kits that you're going to use to be able to leverage that hardware. What you do today is using things that you are already familiar with, like Visual Studio, like Jupyter Notebooks, which I'm assuming people who are technical here use and are familiar with. You are still programming in those environments that you are very familiar with. The hardware is abstracted out for you, such that when the hardware matures, whatever you develop from your code and application perspective is reusable. Okay, so that is one important part of it. But alongside, there are many things which are available in terms of resource estimators, simulators, because when you want to give something to a quantum hardware, you also want to simulate what it will take. So let's keep going. I'm going to go fast on this. So the kind of things, for example, that is possible, I was mentioning to you earlier, with quantum computing is to be able to do simulation of real world. And where that is, for example, useful in chemistry. I gave a few examples earlier, right? I talked about fertilizer, I talked about drug discovery. And so there are work happening to make sure that chemistry people who have deep scientific understanding of chemistry are working closely with the quantum team at Microsoft to create libraries that can be used by others to develop software, develop algorithms. Okay? The second one is optimization. Now, a lot of the problems that we deal with, whether it is a financial portfolio or whether it is logistics, traffic optimization, or loading or distributing a limited resource, let's say bandwidth, or logistics, etc. Many of those are large-scale optimization problems. So what people are doing using quantum is the idea of quantum they are taking as a way to speed up optimization. And this actually is being used by multiple people who are early in this game and are looking to make sure that they are ready for the quantum age when it comes. So I'll share a video on this. Let me see, hopefully it plays. Can you get the audio going? Can you play it? No, it's coming. All right, so I don't think it's playing. So I'm just going to tell you about this, that there is a problem in the world of MRIs wherein you need to be able to determine the sampling size, the kind of exposure you want to give, and it's non-trivial. To solve that optimization problem is actually not possible with current classical computation. Even with GPUs or whatever you might want to have, it's not possible. So what these people in this university are doing is using the quantum-inspired optimization I was talking about to formulate the problem as an optimizer that is using quantum effects to find the best solution. And unfortunately, you can't hear it, but that's okay. The quantum effects it's using are fundamental to the way quantum computers work, which is why we are calling it as overall part of quantum computing, because while quantum computers, the hardwares are still early in the game, it is important to understand how to build algorithms that can leverage how quantum mechanics works. So therefore, even experimenting to understand, and what optimization is doing is finding, if you are familiar of mathematics of optimization, it is finding global minimum using something called quantum tunneling. Don't bother look it up if you feel like it, but it's actually pretty cool. So, anyway, but the point is that I'll move forward from here. Okay, so when I spoke about this full stack approach, right? So what you are seeing here, from a Microsoft perspective, it's part of Azure. So what you are seeing there is quantum and quantum-inspired optimization are not something separate. It's not like a separate computer that's a quantum computer. It's part of the entire software stack. You are going to need compute, you are going to need storage and networking and everything else, databases, everything you're going to need, security, identity, everything you're going to need. You will have a quantum special purpose computer. Like today, you may send off something to a GPU, for example. Like you may send off, if you are solving a large optimization problem, to a sparse matrix solver or something, you will send off something to a quantum computer. Okay? And that is why it is important to take a full stack approach. You cannot do quantum computing if your data is somewhere else. You are going to need the full stack, right? So what does that mean? That means that the libraries, the entire development environment that you will use should be something you're familiar with today, and which is what we're doing. What we're doing is that you use something called Q#. Q# is Microsoft's, Qiskit is IBM's, Circ is Google's. We support all of them. The point being that those are the languages, abstraction languages in which you Okay, so the point being that you want to invest in quantum in a way that whatever you do today is reusable and is accretive. You learn it, tomorrow what you do should reuse what you did today, right? That's the whole point. So in the meantime, while the physics of it is fairly complex, but absolutely, I just get very excited about it. But there is a bunch of universities, including in India. There's much happening in India, by the way, on quantum. There are organizations in certain areas. There are who are using optimization, etc. There are people who are experimenting and doing the quantum overall ecosystem, and there's a network that's building. In fact, there is a fairly vibrant ecosystem that's coming together. Who are these people? These are people who are either customers or partners who are experimenting with quantum. These are universities who are researching, because a lot of the work, for example, like the one I showed you on chemistry, requires the domain experts to be able to formulate the chemistry problem into a quantum problem. Okay? And then there are providers. These providers on the left-hand side who you see are both service providers, they are hardware providers, they are people who are creating solutions on top of hardware. So this ecosystem is building. So what does it mean from your perspective, right? Look, the fundamental part is that quantum is a fundamentally different way of computing. So if somebody is starting in the world of quantum, it's not like you actually have to go back to your physics classes. You have to go back to your physics classes and your math classes. And I love that. So you have to go back to that because you have to learn the basics of how computation happens. So that is why it is a long lead time. You can't say, okay, I was using this language, tomorrow let me use another language. It won't work. You have to go back to your physics and math. And if you love physics and math, that's great, right? So the way it will work is that your time horizon, what is your R&D time horizon? If your time horizon is, 2 years later, I want something that's solved with quantum, please don't. It's not going to happen like that, okay? But the way you think about it is, for the next 5 years, you will look at certain use cases that are a hybrid between a quantum and a high-performance compute. You will look at certain problems which will be solved with optimization that normal other optimizers cannot solve. Okay, even things like simulated annealing and many of the Monte Carlo techniques, etc., those are not able to solve. Quantum is able to solve some of those problems because of certain quantum mechanics it's leveraging inside the algorithm. Okay, you will connect with the ecosystem in terms of technology partners, etc., and you will create the internal capability to leverage this disruptive technology. Now, the one place where you have to pay attention right now is security. Because quantum computing, when it becomes ready, is expected to break RSA, which is the fundamental security protocol that we are using in every single communication in internet, everything. So there are people out there who are thinking about it, the standards being created for what would cryptography look like in the post-quantum era, when quantum happens and is able to break RSA. Okay, that is one of the biggest areas which is like burning platform right now. Okay, if with a slightly bigger horizon, if you are working in that journey, then you are ready to create complex industry-style use cases, and you are able to have the hardware is there, and you're able to actually leverage it. But it is a long game, and it is a long game because it does take that level of investment, expertise, and skill building to be able to leverage it. Okay, so what should, as leaders, you should do is look at your industry and understand what are problems, especially if you are an innovator and you are thinking about certain problems. And I see that across industry. I see in financial services, I see in healthcare, logistics, of course, in many areas. So it depends on the industry, but look at the problems that require optimization today, but also certain computation challenges that cannot be solved with today's classical, especially if you want to solve real-world problems. Look at a team that is interested in quantum, and trust me, there are a lot of, especially my colleagues, etc., who kind of get very excited about this. This is actually very, if you have a sort of geeky crowd, they start to really like this stuff because it is pretty cool. And then look for the ways in which you build your applications, your capabilities that can then get ready for the conventional computers as we go forward, because it's a stack approach. So I'll just stop with that. I've got a bunch of resources if you want to take a picture of this in terms of exploring. There's tons out there. You'll be spoiled for choice in terms of the amount of content and training material, etc., that's out there to work on quantum. I'll see if the next one, if the video plays, otherwise we are out of luck. Nope, you can't hear the audio. Okay. All right, while they figure out any one question I can take, maybe I've got time for any questions, or did I lose you all? Yeah, go ahead.
Let me bring the mic to you.
Hello, my name is Anshul.
Yeah.
And I was listening to in first slide you said that current hardware cannot solve the quantum problems. Okay, later it was mentioned that in Microsoft Azure is having a special section for solving quantum problems. So how are you achieving this? So is it the traditional hardware or you have a system or a new hardware somewhere around which is solving those problems, especially in Azure?
Okay, so let me kind of unpack your question a little bit. When I was initially saying that there are certain problems that cannot be solved by classical, I was making a point. The point is that there are certain class of problems which nobody can solve in the classical computing because they, as the size of the problem increases, the time it takes to solve it grows exponentially. That was one chart I had, right, which the graph was going like this. And so that has nothing to do with Microsoft or anybody. I mean, it is an immaterial, that's the fundamental nature. What I was later on showing was that because we realize when quantum computing becomes real, it will be a game changer. But we can't get ready for it when it happens. We need to be ready for it in a horizon-based approach. Therefore, to be able to build the rest of the software stack, compilers, everything, the development environment, everything else, the data, the storage, the network, everything else, right? We will need all of that, wherein Azure Quantum will be one of the special purpose solvers. When I say Azure Quantum, what I mean actually is, to be able to clarify, is that there is a network of partners that we are building, which I showed in one of the slides, whose hardware will be available. Even today, if you go and try Azure Quantum, you can choose which hardware you want to use. So it could be Honeywell, it could be IonQ, because all of these are having different approaches to even creating a qubit. But you as a software developer should not have to develop one program for the Honeywell computer, one program for the Ion bit, right? You'll be able to write one piece of software that can go into any hardware. That's the point.
Thank you.
Yeah. Okay, you have the audio. Okay, we'll play a small video and then just humor me.
When we talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We could attack global warming.
Security,
What are the boundaries of machine learning?
fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast, and we're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in a billion parallel universes at the same time?
Okay, great. Thank you so much.
Dr. Rohini, Srivathsa, can I please request you to be on the stage? Thank you. I think with this, I've come to a conclusion, Doctor, that there are three kinds of people in this world. One who do understand quantum physics, one who do not understand quantum physics, and the other is a category who do and do not understand simultaneously. So I don't know how many of you fall in that category, but thank you for a splendid presentation. And one thing unanimously that we all agree is that it's irrespective whether you do or don't, we know it's impacting our lives in a huge, humongous manner. So thank you. Now I would like to call upon stage Dr. Rakesh Agarwal, Managing Partner VR Analytics, to do the honors of sharing a small token of appreciation. Please put your hands together, everyone. So we've planted a tree on behalf of you on the certificate. Thank you.